Welcome to my channel Cherish Physics. Subscribe my channel and keep watching. Today let us see the topic surface tension. From the name itself we can understand there is a tension, that is force on the surface. It is implied by the symbol sigma or T. See the picture, a beaker filled with water or any other liquid. The surface of the liquid behaves as if it is covered with a stretched elastic membrane. Mostly this surface is called as elastic skin. In the diagram, let AB is the imaginary line and the tangential forces that acts perpendicular to the imaginary line, and the forces are tangent to the surface of the liquid, so that it is called as tangential force. Due to this tangential force, the surface area gets contract, which tends to minimum surface area. So, surface tension is the property of the free surface of the liquid at rest to behave like a stretched membrane in order to acquire minimum surface area. It is defined as the force per unit length acting perpendicular to the line and tangential to the liquid surface. It can be defined in terms of force or energy. In terms of force means it is force per unit length, and if it is energy means energy per unit area. The formula of surface tension sigma equal to tangential force divided by length. The SI unit of surface tension is Newton per meter. Its dimensional formula is m(T to the power minus 2). Surface tension happens due to the following forces. First one is intermolecular forces. It is the force between two molecules of a substance. Now let us see the molecular theory. First, let us consider the molecule P, which is inside the liquid. So it experiences forces in all the direction. Hence, the net force acting on the molecule is 0. Now let us consider the molecule S, which is on the surface of the liquid. It only experiences net downward force. So the surface gets pulled downwards and hence it acquires a minimum surface area. Next one is cohesive force. It is the force of attraction between the molecules of the same substance. Cohesive force is very strong in solids. It is weak in liquids and extremely weak in gases. Next, adhesive force. It is the force of attraction between the molecules of two different substances. Example, ink sticks to paper while writing. Fevical and gum are also the examples. Next, molecular range. It is the maximum range up to which a molecule can exert force of attraction on another molecule. It is of the order 10 to the power minus 9 meter for solids and liquids. Next topic, surface energy. It is defined as the ratio of work done in increasing the surface area to increase in surface area. Its unit is joule per meter squared or Newton per meter. An important point, surface energy is numerically equal to surface tension. Next, let us see the variation of surface tension of a liquid with temperature. Mainly, surface tension depends on the nature of the liquid, purity of the liquid surface and temperature of the liquid. The surface tension decreases as its temperature increases and reaching 0 at critical temperature. The surface tension related to temperature formula is given here. First one, sigma equal to sigma naught into 1 minus alpha T. Here sigma is the surface tension and sigma naught is the surface tension at a reference temperature, or it is often taken as 0 degree Celsius, and alpha is the positive temperature coefficient of the liquid and T denotes temperature. Second formula, sigma equal to sigma naught into 1 minus theta divided by theta C the whole power n, where theta is the current temperature, theta C is the critical temperature and n is the empirical constant. Mainly, its value is 11 divided by 9. Next is the angle of contact. It is the angle between the tangent to the liquid surface at the point of contact and the solid surface inside the liquid. See the picture. The line R is the tangent to the liquid surface, which is at the point of contact Q, which touches the solid surface inside the liquid. The angle of contact depends on the nature of the liquid and the solid in contact. See the picture. If we dip a glass rod inside water, its meniscus will be concave and hence the angle of contact is acute. But if you dip a glass rod in mercury, its meniscus is convex and its angle of contact is obtuse. Let us see the practical applications. If we add soap or detergent in an aqueous solution, its angle of contact becomes minimum, so the soap solution penetrates well in the cloth and removes the dirt. Next one, waterproofing paint. It enhances the angle of contact, so water does not penetrate through the wall. The angle of contact of mercury is nearly 140 degree. For pure water and clean glass, the angle of contact is 0 degree. For water and many liquids that wet glass, the angle of contact is nearly 0 degree. For water and glass, the angle of contact lies between 8 degree and 18 degree. For most liquid and glass, the angle of contact is less than 90 degree. For the water-silver interface, the contact angle is equal to 90 degree. Here, the liquid-solid and solid-air interface, the surface tension difference is exactly 0. We have to understand that here the surface tension is not 0. Only the surface tension difference is 0 because the surface tension between silver air and silver water interfaces are equal. Next, let us see the excess pressure in the curved liquid surface. See the first diagram. It is the concave surface of the liquid and here T implies the surface tension and R is the resultant force due to surface tension. The resultant force, it acts vertically upwards. To balance this excess of pressure acting downwards. The second diagram shows the convex surface of the liquid and here the resultant force acting downwards and the excess of pressure acting in the upward direction. In both the cases, the excess of pressure acting on the concave side of the curved liquid surface. This implies that there is an excess of pressure on the concave side of the curved liquid surface over the pressure on its convex side due to surface tension. For exam point of view, here I have given excess pressure formula for several cases. First one, the excess pressure inside a liquid drop. Delta P is equal to 2T divided by R. Second one, excess pressure inside a soap bubble. Delta P equal to 4T divided by R. Third one, the excess pressure inside a synclastic curved surface. Delta P equal to T into 1 divided by R1 plus 1 divided by R2. Fourth one, excess pressure inside a synclastic curved film. Delta P equal to 2T into 1 divided by R1 plus 1 divided by R2. Fifth one, excess pressure over the anticlastic surface. Delta P equal to T into 1 divided by R1 minus 1 divided by R2. Synclastic and anticlastic surface has two center of curvatures. In synclastic surface, the center of curvatures are on the same side of the surface. In anticlastic surface, the center of curvatures are on the opposite sides of the surface. Here, R1 and R2 are the radius of curvatures. Sixth one, excess pressure inside a cylindrical drop of liquid. Delta P equal to T divided by R. Seventh one, excess pressure inside a cylindrical bubble. Delta P equal to 2T divided by R. From the above formula, it is noted that the excess pressure inside a cylindrical bubble is equal to the excess pressure inside a liquid drop only when they have same radius. On the whole, it is implied that the excess pressure inside a drop or bubble is inversely proportional to the radius. Next, let us see about the work done in blowing a liquid drop or soap bubble. If we blow a liquid drop from radius R1 to R2, then the work done will be W equal to S into 4 pi into R2 squared minus R1 squared. This equation we obtained from surface energy formula. Here S is the surface energy and the term 4 pi into R2 squared minus R1 squared is the increase in surface area. Next, work done in blowing a soap bubble. Normally, if we see a soap bubble means it has two free surfaces. So, its work done is twice the work done in blowing a liquid drop. W equal to S into 8 pi into R2 squared minus R1 squared. Next, let us see the work done in splitting a bigger drop into smaller droplets. If a bigger liquid drop of radius r is split into n smaller droplets of same size, then its radius r equal to r into n to the power minus 1 by 3. On substituting and simplifying, we get W equal to S into 4 pi r squared into n to the power 1 by 3 minus 1. Next, coalescence of liquid drop. Coalescence is nothing but merging. In the last case, we have seen splitting, and here this one is merging. Here, n small liquid drops are combined together to form a single bigger size drop. So, its radius capital R equal to n to the power 1 by 3 into R. In this process, energy is released, which is delta U equal to S into 4 pi R squared into N into 1 minus N to the power minus 1 by 3. Next, let us see the topic capillarity. If we dip a capillary tube inside a water or any other liquid, there will be a rise or fall of liquid in the capillary tube. It mainly depends upon the nature of the liquid and the radius of the capillary tube. In the case of water, its meniscus is concave and the angle of contact with the solid, that is with the capillary tube, less than 90 degree, so it suffers capillary rise. Water has weak cohesive force and its adhesive nature with the capillary tube is strong. So the degree of wetting the capillary tube is high. In the case of mercury, its meniscus is convex. The angle of contact is greater than 90 degree and it suffers a capillary fall. The cohesive nature of mercury molecules are very strong and the adhesive force of mercury with the capillary tube is weak. So its degree of wetting the capillary tube is low. For a plain meniscus, the contact angle is 0, its cohesive force is weak and its adhesive force is strong, so it has perfect wetting. Next, let us see the surface tension formula in the rise of liquid in a capillary tube. In the exam point of view, I have given only the equations. Surface tension T equal to H plus R by 3 into rho g R divided by 2 cos theta. H is the height of the liquid rise in the capillary tube and rho is the density of the liquid, g is the acceleration due to gravity, r is the radius of the capillary tube and theta is the angle of contact. If r is very small means then we can neglect r by 3. So T equal to h rho g r divided by 2 cos theta. From this equation we can rewrite it for height h equal to 2t cos theta divided by rho g r. From this it is very clear that the rise in the capillary tube, that is its height, is inversely proportional to the radius of the capillary tube. That is, smaller the radius of the capillary tube, greater will be the capillarity, that is rise of liquid. Next topic, method of drops. Stalagmometric method. It is also called as drop count method or drop weight method. It consists of a glass tube with a bulb and the lower end of the bulb has a capillary tube. From that water drops will fall. Here we can compare the surface tension of two liquids by the formula T1 divided by T2 equal to N2 divided by N1 into rho 1 divided by rho 2, which is equal to N2 divided by N1 into M1 divided by M2, where N is the number of drops, rho is the density of the liquid and M is the mass of the liquid. This method is based on Tatt's law. It states that the weight of the drop falling from the capillary tube is proportional to the surface tension and the radius of the capillary tube. W equal to mg, which is equal to 2 pi r into t. Next topic, Quincke's drop method. This experiment is specially designed for liquids, mainly to determine the surface tension of mercury, which does not wet the glass or substrate on which we are going to place the mercury drop. See the diagram. It is an experiment. It consists of a horizontal leveled wooden stand. On that stand, we are going to keep a clean glass plate. In the glass plate, mercury drop is added. The cohesive force between the mercury molecules are very strong than the adhesive force between mercury and the glass plate. The interface of the mercury and the glass plate is in a bending form. In this Quincke's drop method experiment, traveling microscope is used to find the total height h2, that is between B and C, and the height of the drop above the most protruding part, which is equal to h1 equal to B minus A. The surface tension of mercury is calculated by the formula T equal to h1 squared into rho into G divided by 2. And by Quincke's drop method, we can also find the angle of contact. Let theta is the angle of contact of mercury with glass. Its formula is cos of 180 degree minus theta, which is equal to h2 squared divided by h1 squared minus 1. From that, theta equal to cos inverse 1 minus h2 squared divided by h1 squared, since cos of 180 minus theta equal to minus cos theta. Thank you.